Hello, I'm Yoonchang from Virginia Tech. This is a joint work with Ashish, Kumar, Budhiraja, Dr. Ryan Williams, and Dr. Pratap Tokekar. We address the problem of tracking multiple targets using multiple robots that maximize the number of targets being tracked in a distributed manner. This figure illustrates multi-robot multi-target tracking, where there are 3 robots tracking 2 targets. Each robot has a limited sensing and communication range. Each robot has a set of motion primitives. In this example, robot has 5 motion primitives that can choose as a future location. Then the question is, how do we choose motion primitive per each robot so that the number of targets being tracked is maximized? Our approach to solve this problem is to simultaneously choose actions of robots and assign targets in a distributed fashion. We can think of this problem as the mixed packing and covering problem. The relationship between robots and motion primitives is the packing problem, where each robot can select at most 1 motion primitive. And the relationship between motion primitives and targets is the covering problem, where each target must be covered by at least 1 motion primitive. Our problem setup can be expressed like in this figure, where the upper part of the graph is packing, whereas the lower part of the graph is covering. We can solve this in a centralized setting using, for example, integer programming. However, we seek a distributed algorithm. Unlike conventional distributed algorithms, we specifically care about the amount of time we spend communicating. If distributed algorithm requires many communication rounds, say comparable to the number of robots, then we might as well have solved it using a centralized algorithm. In order to do that, we adopt a local algorithm. Local algorithm is a constant time distributed algorithm that is independent of the size of a network. We can also formulate this problem using the integer linear programming. We propose bottleneck problem, where the goal is to assign robots and motion primitives such that all targets are equitably covered. There is a local algorithm proposed by Florin that gives an approximation algorithm with a bounded communication round for the linear relaxation of the bottleneck problem. The algorithm has an approximation ratio, which is a function of h, where h corresponds to the number of communication rounds. We show that the local algorithm can be reduced to solve the proposed bottleneck problem. In this simulation, 5 robots with 2 motion primitives are deployed to track 30 moving and stationary targets. We compare the proposed local algorithm with the greedy approach, which achieves the 2 approximation with order n communication rounds in the worst case. This simulation shows that a local algorithm can perform competitively to the greedy approach. Thank you.